Uh, okay, yeah, I think we can start. So, good evening, everyone. My name is Stanley Pocar. I am the current president of the SEG-UCE FIGEMPA student chapter in Quito, Ecuador. It is a pleasure to welcome you all to this lecture. It is an honor to welcome Douglas Kirwin, an Australian geologist with over 50 years of global exploration experience. He has worked with Anglo-American, Amex, and even Home Mines, where he was executive vice president for over 15 years. Douglas was part of the team that discovered the Hugo Dumet copper gold deposit in Mongolia, earning the PDAC Taylor Lindsley Medal in 2004. His work has led to major discoveries across Mexico, South Korea, Myanmar, Australia, and Papua New Guinea. He holds a master's in mineral exploration and is an adjunct professor at James Cook University, dedicated to mentoring future geologists. Thank you very much, Douglas, for this lecture. To the attendants, if you have any questions during the presentation, please leave them in the chat and we will address them at the end. Without further ado, Douglas, we can start.
Good. Thank you very much, Dalen. And thank you to the student chapter for the invitation to make a presentation for you. I'm absolutely delighted to do that. And thank you to all the other participants that have joined as well. My topic for this evening is unidirectional solidification textures and their implication for metallogenesis and exploration. This has been a topic that I've been interested in for a very long time, and I find these rocks absolutely fascinating. So a presentation for the outline is what are USTs, how do they form, and we'll look at some examples. And then I have also a brief discussion about silica caps and then some concluding remarks. USTs is an acronym for unidirectional solidification textures, and this was first used by geologists working at the Climax and Henderson molybdenum deposits in Colorado in the 1970s. Basically, it's a metallurgical term, and what it means is parallel to subparallel bands of minerals, mineral layers, and in this case, quartz plus feldspar quartz. And the two things to note here is that the upper part of the layer is planar and the lower part is sawtooth. And this reflects crystal orientations. And in the case of quartz, the C-axis terminations. So what we're looking at here is parallel bands of quartz plus feldspar quartz. It's very important to note that these are not vein textures. These are primary magmatic textures. Here's a model of a cupola, a simplistic model, and it shows the position where USTs form, which is at the very top of the cupola. For this presentation, we're going to firstly look at USTs, and then we'll have some examples from silica caps or quartz caps, which are intimately related, both of which occur at the top of a cupola. On the left is an example of a tungsten-bearing cupola from Western Mongolia, and on the right is a cut piece of cupola rock, and the upper part shows the Hornfels sandstone contact. The lower part, the 90% below the contact, is the top of the intrusion, and here we see well-developed USTs. You will note that these are parallel layers of quartz plus feldspar, and when you look carefully at the layer, you can see the bottom part has C-axis terminations of the quartz crystals. We see the same thing in thin section, and here's an example from a porphyry gold copper deposit in southern Mongolia, and we see a nicely developed quartz band in the central part of the slide with the upper planar layer and the sawtooth lower layer with the C-axis of the quartz crystal terminations. How do they form? The stability field of quartz is pressure dependent. And so if we look at the ternary diagram for quartz and sodic feldspars and potassic feldspars, we see the red is quartz, the blue is the sodic, and the green is the potassic. The upper diagram shows normal conditions of pressure. If we go to the bottom left, we see an example of overpressuring, and what that does is expands the stability fields of quartz with respect to feldspar. Conversely, on the right side, we see an underpressured example where the quartz stability field is much smaller than that of feldspar. So pressure plays an important role in the formation of these textures and with respect to the stability field of quartz. What we're looking at here is an example from, on the right, from the anticlimax molybdenum deposit in BC. And on the left, I've attempted to show degrees of overpressuring with time. So if we think about the lid on a boiling pot of water, when the lid comes off the pot, we release the pressure. The lid falls down on the pot, we increase the pressure. And so as we rhythmically increase and decrease the overpressuring, we have the ability to change the stability field of quartz. On the left, there's a graph that shows degrees of overpressuring with time. So at the beginning, the overpressuring is starting to build up and then it increases with time. And that's reflected when we look at the thickness of the quartz bands in this cut slab. So the upper band is thin, and then we increase the degrees of overpressuring and the bands become thicker. Conversely, we can do the same thing with very limited periods of overpressuring. So in this case, on the right-hand side, we have a cut slab from the Red Dome porphyry copper gold deposit in North Queensland. We can see nice parallel bands of quartz, but in this case, the C-axis terminations on the lower part of the layer are only weakly developed. So what we're experiencing here is rhythmic but very limited periods of overpressuring. If we go to the other end of the scale, here we have significant periods of overpressuring with respect to time. So for most of this period, we have overpressuring in the cupola and we form these very thick bands of magmatic quartz. These are still USTs. You can see the upper planar layer here and you see the bottom part of the layer there with the rhythmic C-axis terminations of the quartz. So in this case, the periods of overpressuring are quite large. And this is from the Sagan-Chalut intrusion-related gold deposit in northeast Mongolia. On the government geological maps, this was shown as a quartz vein, which, unless you looked at this closely and were able to interpret it, that's probably what most people would call it. Once again, I stress that these textures are not quartz vein textures. They're primary magmatic. Some of these crystals can be very large, and in the case of Sagan-Chalut, some of these individual crystals are perhaps 10 to 15 kilos or more. Here's another form of UST textures. In this case, it's not parallel to subparallel bands. What we're seeing here is rhythmic growth of individual crystals. And on the left is what some people call herringbone textures. And we're looking at rhythmic quartz formation within an individual crystal. And we're actually looking down the C-axis. We're looking along the C-axis of the quartz crystals. If we look down the C-axis of the quartz crystals, what we see the same thing, rhythmic growth, but it has a totally different shape. And this is from the log tongue tungsten moly porphyry in the Yukon. So whilst these are not nice parallel to subparallel bands, they are still unisolidification texture growth. This is an even better example looking down the C-axis of some UST quartz, and this is from a tungsten deposit in North Queensland. Very nice example. Tin deposits also have UST textures, and much the same as we saw in the previous slide. This is from quite a famous tin mine in the Erzgebirge district in Germany. Another feature that one sees is what I call atoll textures, and here we have an example from the San Lorenzo copper district in central Chile, and what we're looking at here is rhythmic growth of quartz and magnetite. If you think about a cabbage and you take a horizontal slice off the top of the cabbage, all of the leaves that you would see looking down on that top of the cabbage would have parallel to subparallel wavy circular bands. And we see the same thing in USTs. So these are three-dimensional features, and they form in the very top of a cupola. On the left, this is an example from a tungsten deposit in Canada, and we see UST textures on the left side, which has undergone clearly severe overpressuring. We then return to normal pressure conditions, and we no longer have the ability to form USTs. What one does see in some of these rocks, where there's no actual USTs, but if you look carefully at the quartz phenocrysts, you can see that they're embayed and they're somewhat globular or circular. This is an indication for overpressuring in porphyritic rocks. So it's always a good idea to look to see what's the morphology or the 3D geometry of your quartz phenocrysts. If they're nicely bipyramidal, then this rock hasn't undergone any degree of overpressuring. If they're globular and circular like this, then that's probably a result of overpressuring conditions. These can be extremely subtle, and it requires very careful examination, especially with drill core. So here's an example from the Resolution porphyry copper moly deposit in Arizona, and if you didn't look very carefully at this rock, you could easily miss these subtle features. So in the central part of this slide, we see very nicely developed convoluted quartz layers, and we also see those nice sub-rounded and embayed quartz phenocrysts that I mentioned. When you look at these, once you get your eye in, you can start to see them all through the slide, but very easy to miss if you don't look carefully and you don't have an appreciation of what these textures look like. An example from the field, this is from a copper moly porphyry prospect in Victoria, Australia, and if you were just walking along in the course of your mapping, you could easily miss this, and the question is this a UST texture? And once we look carefully at this sample, we can see that there are convoluted bands of quartz, and we can see an atoll texture here, and over here on the far right is actually a quartz vein. So this sample shows magmatic UST bands overprinted by hydrothermal quartz veins, all in the same rock. And this just reflects the evolution from high pressure and temperature to lower pressure and temperature. If we move to Namibia, there is a very well-exposed cupular complex called Spitzkop, and near the contact of these cupulas, we see very nice orientated bands of plumose feldspars or wedge shapes. And looking at this layer, you can see the feldspars, and they, near the contact, they start out as essentially a very thin crystal, and with growth, this crystal expands into a wedge shape. And so these have unidirectional growth, and this is another example of USTs. this is from the same area, and it's a much clearer example. And so when you look at this rock and the orientation of these feldspars, you would know that the contact is at the top of the slide. Another example from the Sinsalar tin-bearing district in northern Saudi Arabia. Beautiful examples of plumose feldspars, and in this case some of them show branches of growth, almost like corals. Beautiful contact UST textures. A more exotic example is from the Altenburg tin cupola in the Erzgebirge in Germany, and the yellow and black cupola zone is comprised of topaz and zinwaldite, and we see the same thing as the feldspars, but this time with wedge-shaped topaz crystals. It's more, this is quite rare, but it's a nice example, and I found it quite interesting. I mentioned very early in the presentation that USTs were first, or thought to be first, recognized by geologists working at the AMAX, Climax and Henderson molybdenum mines in central Colorado. And this was in the 1970s. And they started seeing these contact features in their underground mapping and recognized them as cupola textures. And they made these beautiful internal reports thinking that these were very diagnostic for porphyry molybdenum deposits. And this was in the 1970s. At the time, I was working with AMAX, and I was exposed to some of this in-house research, and it was extremely interesting. So for about 5 years, AMAX spent a lot of time and effort looking globally for other climax-type molybdenum deposits, and specifically looking for these specific cupola textures. Some of this work was eventually published quite a few years later in 1982 in a very good paper in the Geology magazine, and it described all the different features that were obviously seen underground at the Henderson molybdenum mine. Much later, when I started looking into this, I discovered that there was a Russian lady geologist who in the 1950s was working in tungsten deposits in Transbaikalia in southern Siberia, and she actually did her PhD in 1951. I was able to eventually get a copy of some of her work, and it was a fantastic piece of work. And this is 25 years before the AMAX geologists were working at Henderson. And on the right is a diagram from her thesis, and what this shows is the fantastic variation in these textures. Number one is pretty much the first or second slide I showed you with the beautiful horizontal parallel bands. If we go to number 9, there's the atoll textures, and there's all the other variations that one can see. Unfortunately for this lady, as a woman in Soviet Russia at the time, she didn't get to publish this till many years later. But importantly, she recognized these textures as cupolas, and also she understood clearly their exploration significance. This is an interesting photo. After I left the US, I was still working with AMAX, and I was based in North Queensland, Australia. And at that time, a friend of mine, good friend of mine, Max Baker, was doing his PhD on the Kidston gold-bearing breccia pipe in North Queensland. And I'd go up and spend a few days with Max while he was mapping as part of his PhD. And he mentioned to me one day he wanted to show me a very interesting outcrop on the side of the hill. What we're looking at here is the Wiser's Hill gold-bearing breccia pipe, hydrothermal pipe, before it was mined. And so this entire hill is hydrothermal breccia, and the green star represents an outcrop of breccia that Max wanted to show me. And there was a clast about the size of a small car. and it was a UST. When we cut this rock and looked at it, it was very obviously subparallel bands of quartz with orientated crystals. So this possibly was the first recognition of these textures outside a tungsten molybdenum environment, and more specifically in a gold-related system that had nothing to do with porphyry moly. At the time, I was with James Cook University, and there was an active school there. Also in Canada, Dave Sinclair and Rod Kirkham were working on tungsten deposits, and they published a very good paper on some of the deposits that they've been working on. And there were many, many occurrences of USTs, not anything to do with a climax type molybdenum deposit. At James Cook, there were a number of students working on gold deposits in northeast Queensland, and one of these was Chris Torrey, who was working on the Red Dome deposit. And in the drill core he was studying, there were a lot of USTs as well. So all of a sudden, it was appreciated that USTs weren't specific to climax molybdenum deposits. It wasn't a silver bullet, and they were in fact a relatively common feature in cupolas which had overpressured volatiles and fluids. In the last 20 to 30 years, there's been a number of these now recognized throughout the southwest US porphyry district. And there's a few examples. I showed you one from Resolution. There are many. And in fact, so they're relatively common. They just simply haven't been recognized. Quickly, a little bit about Mineral Park, which is on the top left of your slide there. That's a very interesting porphyry copper moly deposit. And here's an aerial view of that deposit. It was mined basically from the 70s to about 2000, open pit mining. And the feature shown there with the oval yellow ring is the top of a cupola. And it's shown here just in the central part of this slide. And when you look at these rocks, here's what they look like. And in fact, Dick Nielsen, when he was mapping this area 70 years ago in a paper, he published a description of crenulated quartz, which is in fact was a UST. They just simply weren't understood at the time. So these two cut slabs clearly show well-developed USTs associated with this cupola at Mineral Park. Another variation on this is what I actually call dendritic-like USTs, and this particular band here, whilst it doesn't show well-developed quartz crystals with nice C-axis orientations, it just shows globular, irregular growth on the lower part of the band. And I've tried to blow that up a little bit on the top left. So this is still very much a UST texture. And this is from a copper gold porphyry in New South Wales, Australia. What I'd like to highlight here is that in this slide, overall, we can see very nicely developed subparallel bands of magmatic quartz or USTs. If we only saw the field of view within this yellow ovoid, it's not easily recognizable as a UST. Yes, it's a cupola texture, and it is part of a UST horizon. And I just wanted to highlight the tremendous variety one can see when looking at these textures. It can be difficult to distinguish whether these are cupola features or are they hydrothermal quartz veins. And one of the things I use is there very irregular convoluted quartz bands, or do you see distinctive vein textures? And in this case, I don't see any distinctive vein texture per se, and so I would interpret this as a cupola texture. There is a gradation from USTs to A veins, and that simply reflects a drop in pressure and temperature, transitioning from magmatic to hydrothermal conditions. This is beautifully shown in a very large cut slab I have from the Hungut copper porphyry in the South Gobi in Mongolia. And in the central part of this slab, we can see quite nicely developed USTs with upper planar surfaces and C-axis terminations pointing to the bottom left of the slide. As we move outside the red marker, we no longer see nice, well-developed UST growth directions, but we still see parallel bands of magmatic quartz. So here's the direct transition from well-developed USTs to simply magmatic subparallel bands of quartz and eventually into hydrothermal conditions. There are many examples of these rocks, of these textures, from the porphyry gold copper deposits in the Lachlan Fold Belt in New South Wales, Australia. And I'd like to just briefly highlight North Parkes and Ridgeway. These are mid-Paleozoic porphyry deposits in the Lachlan Fold Belt. So in the drill core, here's some of the textures that we see. And this is from one of the Endeavour deposits. And as I commented earlier, is this a quartz vein or is it a magmatic cupola texture? And my interpretation of this would be that it's more magmatic than hydrothermal, because we can't see any specific vein development, and some of these quartz have actual crystal boundaries. Here's yet another variation, and we ask ourselves the same question, and I interpret this as a cupola texture, and it's basically a poorly formed UST horizon with some disruption and some overprinting of hydrothermal quartz veins. There's the dendritic variety that I showed you earlier, a few slides earlier. This too is a cupola texture, and it's telling us that we're at the top of the mineralized intrusion. Here there's no actual banding, but what we're seeing are those very convoluted, embayed quartz phenocrysts. And this is an indicator, for me, this is a direct indicator of massive overpressuring. So we have both, in this drill hole, we have both USTs and we have these very irregular, unhappy quartz phenocrysts. Here's another one from the E22 porphyry. And in fact, these are relatively common in pencil porphyries. So it's important to recognize what they are and decide, based on good observation, whether these are hydrothermal quartz veins or magmatic cupola textures. If we go now to Ridgeway, which is up there on the top left of the slide, there are some beautiful examples of cupola textures at Ridgeway. It's basically a pencil porphyry, and Alan Wilson did his PhD on this deposit a number of years ago. It was a great piece of research, and what he found at Ridgeway at the top of the pencil porphyry were some absolutely fantastic mineralized quartz UST horizons, and in this case the chalcopyrite is within the quartz bands, and what we know now, we can determine the growth direction, because basically there's the upper planar layer, and we look at the bottom layer and we see this sawtooth C-axis quartz terminations. So this is a beautiful example of a highly mineralized UST at the top of a cupola. In terms of dimensions, you might be wondering, well, how big are these UST horizons? Typically they're not very big, and they're normally at the top of the cupola. They could be anything from a few tens of centimeters to a few meters thick, and they could have strike extents of a few meters to, perhaps in the case of Climax and Henderson, more than 100 meters. But typically in 3D, they're relatively small, and they occur at the top of the cupola. there's a closer up view of the same area, and we see the nice terminations. We see chalcopyrite and bornite intimately associated with the magmatic quartz. USTs have now been recognized in most felsic intrusions that have overpressured volatiles and fluids. And this is from the Ad-Duwahi gold mine in the Arabian Shield. It's an intrusion-related gold deposit. It's around 650 MA. And here's a cartoon of that deposit from work done by Jeff Dobridge on the mine. And the mineralization has associated, it's just orogenic essentially, but it's originated from a gold-rich cupola that had nice USTs at the top of the cupola, and in the drill core, here's an example of what's seen at Ad-Duwahi. So this is the magmatic phase, which later transitioned into an intrusion-related orogenic gold system. Another interesting gold deposit is the Hadasamu Bilahi gold mines in Inner Mongolia in northern China, and it was a fantastic place to work. A lot of the original culture is still preserved there, and the local people live in these traditional gers. It's still, it was part of Mongolia and became part of China around the early 1900s. And there's a cupola well exposed at Hadasamu, and what was mined initially at this deposit was the actual contact of this cupola. It was mined for its gold content, and here's a closer up view of some of those workings that go around the periphery of the cupola. And here's what you see when you cut a slab of these cupola rocks, and we can recognize this as a UST. And all of the black material here is magnetite. So we have a quartz magnetite UST, and this particular slab assayed 12 grams gold. What I've observed over time is that when you see magnetite with USTs, it indicates oxidized magmas and hence potential for gold. Here's a few more slabs from that same area, and partially and well-developed USTs, but most of the gold is actually occurring in micromarulitic cavities between the UST zones. In the field, there are recognizable UST outcrops and lots of cupola rocks with mineralized marulitic cavities, as shown on the right. Working there in 2003, there was a small underground mine, and at the time I was working for Ivanhoe, and we tried very hard to acquire this property because we recognized that it was a highly gold mineralized cupola. The bottom shows some of the cut slabs from the dumps, and quite nice gold mineralization in mush textures with some USTs. Later, the Gold Bureau eventually opened this up. The government opened up as an open pit mine around 2009, and essentially they mined the entire cupola. And what we see in this section is the red dot line represents all the UST textures and mush textures, which was essentially the ore, and the green line was the greater than 3 gram gold shell. So this was a highly profitable mine where they actually developed the apex of the gold-bearing cupola. This shows some of the sections, the mine itself just before it closed, different generations of quartz, magmatic quartz, and the gold, a lot of the gold was actually crystalline and magmatic. This is a satellite image that I came across a few years ago. It shows the open pit, and now this has been mined out. But I don't believe this is a one-off type deposit. I believe there should be others like this elsewhere. Now some examples closer to home. There are several known examples from Ecuador, and Misa's kindly sent me some samples from there and photos. and we have the Pigili deposit in the south. And here's some of the nice UST examples from the Ajuai porphyry copper gold deposit that was sent to me by MESA. Some more examples. And in this case, we see two things happening. We see the magmatic UST bands, and they're cross-cut by classic centerline porphyry copper type veins. So we're looking here at both the magmatic component and the hydrothermal component of the system. This is some examples from Colombia that were sent to me by Eric Seedorf, and much the same thing. So these are now starting to be recognized in many, many of the porphyries in Latin America. Closer up view of the Nueva Chiquero deposit. And in this case, like Ridgeway on the right, we can see that chalcopyrite is intimately related with the magmatic quartz. Just briefly now, here is a table of examples where UST textures have been observed. You can go through this later at your leisure, but the point to note here is that they occur in many intrusion-related, felsic intrusion-related ore deposits, not as originally thought restricted to the climax type moly deposits. So they occur in many, many different environments. And I'll leave this to you. You can look at this at your leisure later. The exploration significance, here's a few takeaway points. When you see these textures, it's telling you that you're in an environment where there are fertile intrusions with overpressured volatiles and fluids. It's telling you what level of a system you might be looking at. They may or may not be mineralized. And it's also indicating that there's potential for other target models, because once you have overpressured volatiles and fluids, if that event continues, potentially you form breccia pipes, sheeted vein stockwork type deposits, or if the fluids and volatiles are contained, you form disseminated deposits. In most cases, the UST horizons are barren, but that doesn't mean to say that you're not in a very prospective area for regional scale exploration. They're often unrecognized, and they are generally, or up until perhaps the last couple of decades, they've been misinterpreted. So now just to the second part of the presentation, we're going to move on to another cupola environment where we see magmatic silica or magmatic quartz caps on overpressured felsic plutons. And this is evident. I want to show here the evidence for the magmatic to hydrothermal transition. This example, which is a very good one, is from the Alsuquian cupola and the Arabian Shield, and we're actually driving up here to the top of a cupola which has a magmatic quartz or silica cap, which is actually relatively obvious even from a distance. So for this part of the presentation, we'll go back to the cupola model. We're going to look at some examples and observations in porphyry systems, and then some concluding remarks. Sorry. So here's the cupola model once again, and just to refresh, we've already discussed about USTs, and here is the silica cap, which is comprised of massive magmatic quartz. The geometry, the 3D geometry and level of emplacement of cupolas has some economic significance in that those that are emplaced at relatively deep levels tend to form much broader cupola zones, whereas those that are emplaced at perhaps 2 kilometers to 1 kilometer below a paleo surface have a, or could have a pencil shape. And so if we take the same metal budget in terms of tons and grade, we have potential to form the higher grade deposits in the more pencil shaped deposits. It's not cast in stone, it's a generality, but it's often the case. This is a particularly good example of a magmatic quartz cupola. It's from the Sagan-Savaga district in the South Gobi. It's adjacent to a major porphyry copper deposit, several 100 million tons at around 0.6 copper. And if we go back to the stability diagram, how I think these massive silica deposits form is that you just have one period of massive overpressuring with time. So instead of having rhythmic fluctuations in overpressuring, we just have one big bang event, and this upsets the stability fields of quartz to the point where we only basically have the ability to form massive quartz. In this case, the Sagan-Savaga cap is approximately 50 meters thick and 200 meters in diameter. So it's a very large distinctive feature. In many cases, when you look carefully at these massive quartz or silica caps, at the base you see the transition from massive silica to UST formation. And this is from another porphyry district, Zun Mod in the South Gobi in Mongolia. The upper part of this slab is all massive quartz, and then as we drop the pressure and fluctuate the pressure, we transition into more classical UST quartz bands. These have been observed quite some time ago throughout the globe, and there's a very interesting paper on the Sadersdorf tin deposit in the Erzgebirge district in Germany, and a beautiful section in this publication shows a very clear silica cap or quartz cap shown right at the top of this particular tin-bearing intrusion. And in the German literature, these are called Kurzglockers. There's several of these known from the Erzgebirge and indeed in various other parts of the world. A great example is from the Panasqueira tungsten deposit in Portugal, and in a very detailed paper by Kelly and Rye in Economic Geology in 1979, they clearly show a massive quartz zone at the top of the cupola, which in fact is a silica or quartz cap on top of a tungsten-bearing cupola. In their paper, they also have some nice sections which describe the quartz cap, and then they talked about zebroid muscovite quartz layers. This is in 1979, and in fact these were USTs. And underground, that's a photo from Reimer Seltman, we see these fantastic development of very thick classic quartz UST bands. In a gold district, this is the Ravenswood Goldfield in northeast Queensland, Australia. There is a spectacular quartz outcrop, and it is a massive silica cupola, quartz cupola, and this is sitting within a district that has approximately 5 million ounces of intrusion-related gold deposits. If you sample this, you would get absolutely nothing. The reason being because it's the magmatic pre-mineral event that took place during the evolution of the intrusion-related gold deposits. Some nice examples elsewhere in Saudi. I mentioned Silsila earlier, but we'll go back to Al Suqyan, and this is from a paper by Bukhari et al. In '86, and they have a great section that shows a cross-section of the intrusion, and they called the grey area at the top there is a selexite cap. That's merely another term for a massive silica zone or massive quartz zone, and then underlying that they portrayed a well-developed UST zone. I actually had the opportunity to visit this area, and what we see here is the upper part or the top of the hill is all magmatic quartz. It's a silica cap, and then coming down to the base of that silica cap, forming an annulus, is a nice UST layer. But at the top of the hill, this was intriguing because there were several areas where there were massive quartz crystals. You can see the size of some of these quartz crystals, probably several tons, sitting within massive quartz. And I really have yet to understand how this occurs, but I've seen this now in a number of massive silica or quartz caps. Here's the UST zone at the base of that massive silica. These are Neoproterozoic rocks, but we can still see well-preserved UST bands at the base of the massive silica. In another part of the shield is the Cinsalat Gryson tin deposit, and there was a place that was called Quartz Hill. It's pretty obvious where that is. And then when you go to the hill and look at the base of the silica, we see once again a transition from massive quartz into UST layers into plumose quartz feldspar. And there were some, if I'm not mistaken, yeah, okay. Now we come to the porphyry environment, porphyry copper environment. Pardon me. This is in southeast Queensland, Australia, and there's a deposit there that's being explored by a company called Canterbury Resources, and they're drilling a number of Permo-Triassic porphyry copper molybdenum deposits. And in the field, what one sees there, there's a great example of a massive silica cap shown there with the arrow. I'll come to that in a minute, but this is the typical terrain one would see working as an exploration geologist in much of Eastern Australia. So now we come to that outcrop, and the upper part of that outcrop is all massive quartz or a silica cap shown there above the red line, and then that transitions into an underlying UST layer. There's the massive silica closer up, and this in fact is highly mineralized. It's something like 1% copper. So here's an example of a massive quartz silica cap in a porphyry environment that's well mineralized. And below that, there is a very well developed UST horizon. So once again, a transition from massive quartz silica to well-developed USTs. And in one of their drill holes, while exploring this deposit, they encountered a zone of massive silica, which later was interpreted as a silica cap. And they encountered 17 meters thick of this massive silica, and it assayed 1% copper. Please bear in mind that this is not a quartz vein, which it could be interpreted during the logging, a thick quartz vein, which has happened more than once before, but this indeed is the top of an intrusion that has nice copper, porphyry copper mineralization. Moving to Mongolia, and I'd like just to have a few minutes to talk about Oyu Tolgoi. All the stars there show some of the known porphyries, and there are actually many of them, and they're different ages. Oyu Tolgoi is late Devonian. Hamogtai is Permo-Triassic, so there's a wide range of porphyries, gold copper porphyries in the South Gobi and Mongolia. This is Oyu Tolgoi, and the cross-section shown here is a 12-kilometre long zone, basically south looking north, and it shows the various porphyry gold copper deposits that are now known at Oyu Tolgoi. By far the highest grade one is the Hugo Dummett zone, which is now being mined by underground block caving, shown there in the yellow star. The highest grade part of the Hugo Dummett deposit is actually a monzonitic cupola, and it's comprised of a quartz monzodiorite, And so on the left here, the red outline is the pencil-shaped quartz monzodiorite intrusion, and all that area in blue was termed the QV90, and that simply was described as a quartz vein density of 90%, and this was 25 years ago. In hindsight, and going back and looking at some of the core photos, one interpretation would be that this was actually a massive quartz silica cap on top of the pencil. And the reasons for thinking that are twofold. One is that there's actually no mineralization in the quartz. All of the bornite chalcopyrite mineralization is in fractures. And secondly, looking carefully at this drill core, there's no obvious vein textures. unlike most porphyry copper deposits where the higher grade tends to be related to the best hydrothermal porphyry type veining, this is just massive featureless silica that was shattered and then injected with bornite chalcopyrite mineralization. And here's an up view of some of those upper part of the QV90, and as I mentioned earlier, the quartz is basically barren and all the mineralization is sitting in fractures. So there could have been an early pre-mineral silica quartz cap development, and as that transitioned into hydrothermal conditions, the cap was shattered and it was injected with chalcopyrite and bornite. Another great example of a massive quartz silica zone is that of the Lana Carina project in central Chile, which is essentially a series of magmatic to hydrothermal breccia pipes sitting above cupolas. Here's a section from Lana Carina, and as I mentioned, there are a number of breccias. These are hydrothermal breccias which at depth transition into magmatic breccias, and they're sitting on top of or adjacent to a very large silica cupola. What was interesting about this deposit is that quartz silica cupola had 85 meters at 0.13 moly, so the cupola is highly mineralized. The massive silica cap is highly mineralized. There's the intercept that I mentioned earlier, shown there in purple, the 85 meters. And here's what the drill core looks like. So from approximately 542 meters down to 617 meters was all massive, featureless, textureless silica. And at the base of that massive silica zone, there's the upper contact. It's pretty sharp. And then we had all the massive silica. And then right at the base of the massive silica zone, there was some poorly developed but distinctive USTs. So once again, this isn't a hydrothermal quartz vein feature, which is what it was originally interpreted to be. It's a silica cap, massive quartz silica cap. Now, this raises something, an interesting exploration perspective, because massive quartz outcrops are not that uncommon. And often these are targeted for companies looking for industrial quartz or silica for the piezoelectric industry. And this is an example from northeast Queensland. It's called the Lighthouse Massive Quartz Deposit. And it begs the question, okay, is this a silica quartz cap related to an intrusion that has district potential for magmatic hydrothermal porphyry deposits? Is it an orogenic concentration of quartz, or is it something different, metamorphic perhaps? And one way to look at this, there's a couple of things we can do here. One is to try to look at the base of these massive silica or quartz outcrops to see if there's any UST zones. And if we go back to the case of the Ravenswood district, there are examples of massive quartz or silica cupolas, and you can actually see the contact, and you see that it transitions into UST horizons. So if we see that in the course of our field mapping, we know that we're in a district that has potential for intrusion-related mineral deposits. Something else that can be done, and it's useful but not totally diagnostic, is to look at the trace element contents of these massive quartz or silica cupolas, and there's some distinctive aluminum to titanium and also germanium titanium aluminum ratios, and this is presented in a number of papers, including one by myself and co-authors last year. So like the porphyry examples, here's examples of, like UST examples, here's examples of silica, a typo there, or massive quartz caps in many different intrusion-related deposit environments. So they are extremely interesting. And some concluding remarks. USTs and magmatic silica quartz caps are often formed in felsic cupolas, and they clearly indicate overpressured volatiles and fluids. And these occur in a variety of metallogenetic settings. They can be mineralized or unmineralized, subject to the timing and conditions of the magmatic to hydrothermal transition, i.e. when the periods of overpressuring took place. Typically, it's pre-mineral, but not always. And so it wouldn't bother me at all to sample a magmatic silica quartz cap and get nothing, but I would certainly look within 4 to 5 kilometers, a radius of 4 or 5 kilometers around it, to see where is the post-magmatic hydrothermal potential for intrusion-related deposits. And they're important district scale exploration vectors, as I just said. So that's the end of the technical presentation per se. Later you could look at this paper if you wanted to get more information. What I'd like to do now is just spend a few minutes passing on some of the things that I've found useful in the course of my exploration career. So here's a white rock, and the question is, what is it? Well, just looking at this, we really can't tell. Now, if we cut this rock with a diamond saw, and this is actually the same rock, now it's cut in half, and what we can clearly see now is that it's coliform banded, low sulfidation epithermal vein with beautiful adularia, and this is from the high-grade Sleeper gold mine in Nevada. So simply by cutting the rock with a diamond saw, we can see a lot more textures and interpret the rock with much better information. The same thing here. This is the Monza diorite, and this is from Ad-Dawahi. We're looking at a piece of drill core, and we're looking essentially down the C-axis, like so. Now, if we take the same piece of drill core and we cut it, and this is the same piece of drill core, which was later cut, then here's what we see. So just by cutting the rock, we obtain so much more information to base any possible interpretations. This is the same piece of drill core, just looking at a cut piece and a non-cut piece, and what a difference it makes. Similarly, in weathered outcrops, this is from a gold district in East Mindanao in the Philippines, extremely clay altered, difficult to interpret much. If we take a piece of this and cut it, all of a sudden we can see so much more. What we can see here is that it has clasts, rounded to sub-rounded clasts of different composition. It has a high percentage of matrix rock flour, and potentially this might be a diatreme breccia. So by simply cutting the rock, we see so much more. If you are in an area, perhaps in southern Ecuador, Colombia, Papua New Guinea, and you don't have access to a diamond saw to cut your rocks, what you can do is what I call the poor man's diamond saw. And so on the left is a grinding stone. And generally speaking, in these remote environments, and especially the tropics, the local inhabitants use grinding stones to sharpen their bush knives. And if we took a grinding stone and a piece of rock, we look for the flattest part of the rock. We turn it round, we work out where the flattest part is. We take our marking pen and we put a big X over the flattest part of the rock, like so. And then we take that down to the local village. We have maybe a bucket full of these rocks, 20 or 30 from the course of our mapping. And we discuss with the head of the village that we'd like to contract some of the local people to grind these rocks so that the X is completely gone. Then, once the X is completely gone, we have a very nice flat surface to interpret your textures. So I've found that, and still do, I still use this today, and I found it extremely useful. Rock slab libraries are critically important in major exploration programs. I first saw this at the Henderson molybdenum mine in the 1970s, and I'm pleased to say that this library is still beautifully preserved. So all the exploration project samples were cut so that geologists could get a very good look at the rocks for interpretation, and then these basically are stored in, for want of a better word, a rock library. Here's an example from Ivanhoe's exploration base in central southern Mongolia. We had rocks slabs from all of our projects, and at the end of the day the geologists could sit down and discuss them collectively. Also very useful for orientation for new geologists coming into a project, so that everybody's calling apples apples and not apples and oranges. Another example from an epithermal exploration program in South Korea, and in this case all of the outcrops, veins, etc. were slabbed, and with the assay sheet going back to the slabs you could see character sample the rocks and see which were gold bearing, which weren't, so what was important, what isn't, but a very, very practical and useful thing to do in exploration. I can't overemphasize the value of networking. The more that the younger generation, students, early career professionals, and in fact any stage of your career, the value of networking is critically important, because you expose yourself to new contacts, you always learn something. And here's the Prospectors and Developers Association of Canada meeting in March this year, where there were 27,000 delegates. This is a 5-day opportunity to meet a number of people, and a great opportunity to learn about different projects, etc., etc. Here are some highly recommended economic geology webinar sites. You can look at these at your leisure later. The one good thing that came out of the pandemic was the creation of these webinar sites, and there's a treasure trove of information in hundreds of webinars about economic geology, geology careers, whatever, and particularly the Geologic Society of South Africa. These aren't specifically orientated to economic geology. They're about geology careers over a spectrum of different aspects. GeoHug is particularly good, and for anyone that wants to find out information quickly about an ore deposit, portergeo.com is the go-to website for that. There are thousands of global ore deposits with a one-page summary about the geology, mineralization, etc., etc. So that's very useful. Mindat.org is by far the best site to go to find out information about any specific mineral. Lots of photos, huge amount of information, practical information, and extremely useful. Here's something else that I highly recommend. The New Gen conference is held every 2 years in Perth, Australia, and it's a geology conference attended by geologists who present discovery case histories of multi-million ounce gold deposits. And these papers are presented in a volume, and it's the real story about how these deposits were found. The discovery case histories, what worked and what didn't. These can be accessed, purchased at the website there, New Gen Gold. And just from 95 to 2023, there's 230 discovery case histories about how these particular gold deposits were found. So for anyone in exploration, and especially the gold space, these volumes are a must. I like to read. There's many, many great books out there that you can mostly get from Amazon about companies. There's the top left is Newmont. There's Anaconda on the right, who in their early days after Butte went to Chuquicamata and El Teniente. It's all about their history. The Diamond Seeker is one of my favorite books about exploration persistence and how one of the largest diamond pipes in Africa was found. Here's a few more. The top left is the history, the corporate history of tech. Many, many great books. And exploration discoverers, there's several books written by people who are willing to share their exploration or their mineral discovery stories. And there's one in particular that I highly recommend. If you only read one of these books, It's the one there on the bottom right, and it's published in Geochemical Perspectives, and it's basically the autobiography of Dick Sillitoe, whom in my generation is probably the best and most successful mineral explorer. So this is a great inspirational read. So I think with that concludes my presentation, and I would be happy to take any questions. And I've also, my email is there, so if any of you would like to contact me anytime, please don't hesitate to do so. So thank you very much.
Thank you, Douglas. That was an awesome presentation. Really high quality samples, especially that from Ecuador. First time I see a UST from Ecuador. I really like it. It's quite hard to find that. So there are some questions on the chat. I can read it for you, or if you wish,
Yes, please.
you can also. Yeah, okay. Okay, Joseph said, what are the primary conditions required for the development of UST textures, unidirectional solidification texture? The primary conditions.
Yes, the primary condition is a confined space in the top of a cupola where you have overpressured volatiles and fluids. The best analogy I can think of is a pressure cooker. So you have a pot on the stove and you have the lid firmly fastened. So as the fluids in the pot are boiling, they can't escape, and you're building up massive overpressure at the top of the pot. That's the perfect environment for forming USTs. Now, if you periodically release the pressure by lifting the lid on the pot, so you do this to the pot, you lift the lid, put it down, lift the lid, put it down, lift the lid, put it down. There is your fluctuation in overpressure. And that's my simple explanation. It may not be totally correct, but that's my explanation for the correct environment for forming these kinds of deposits. And in the geologic world, instead of lifting the lid off the pot, you're periodically fracturing the Hornfels carapace at the top of the cupola.
Okay, thank you, Douglas. Another question from Goyo. Are they common, these type of textures, in any kind of deep intrusive, or is it characteristic just in the formation of mineral deposit? Could it be possible to use these textures to differentiate between barren or enriched deposits?
That's a really good question. I've seen examples where there are very large silica caps where I haven't found any mineralized intrusives in the area. Maybe I didn't look carefully enough, but I suspect that they were essentially dry systems, so they didn't have a significant amount or any amount of hydrothermal metal-bearing fluids, just overpressured environment, where in other cases, especially the porphyry environment, porphyry copper environment, or any porphyry-related deposit, you have or can have mineralized massive quartz silica caps, or you can have barren quartz silica caps with mineralized porphyry intrusions in the district. And there are numerous examples of, I only showed a few in this presentation because of time constraints, but there are many examples in districts where you have barren, massive quartz silica caps, and within a radius of 5 to 10 kilometers, you have very, very significant high-grade porphyry copper, moly, gold type deposits. There are many examples like that. So it wouldn't discourage me at all if I drove up to a massive quartz silica cap, I sampled it, I got nothing. I would draw a square around that outcrop with a 5 kilometer radius, and I would prospect all around that area.
Okay, thank you, Douglas. Another question from Marco. Can USTs be found in epabyssal environments? If so, what are the implications for interpreting the magmatic hydrothermal system?
I missed the first part of the question, I'm sorry.
Can unidirectional solidification textures be found in epabyssal environments?
Could you, I'm sorry, my hearing's not that good. Could you kindly spell that for me?
Can unidirectional solidification textures be found in epabyssal environments.
What kind of,
Hypabyssal.
I'm not getting the word right. Environment? What kind of environment? Sorry?
Hypabyssal environments, not intrusive environments. So
Oh, no.
hypabyssal
By definition, absolutely, by definition, they only occur in cupolas and not outside. You won't see them outside the wall rocks, in the wall rocks out. They're only, by definition, they are cupola textures.
So you won't find them in volcanic environments.
Subvolcanic, yes, but that's it has to be an intrusion, a cupola.
Yeah. Okay.
Yes. Yes, rhyolitic porphyries, pencil-shaped rhyolitic porphyries are good environments for forming USTs, but they're intrusive, not extrusive rocks.
Okay, another question from Miguel. How can USTs help distinguish between different stages of mineralization?
Well, as I tried to show, they occur both in magmatic and hydrothermal. Mineralization can be magmatic or hydrothermal. Mostly it's hydrothermal, and thereby it's an event, a hydrothermal event, which overprints the earlier pre-mineral magmatic UST event. So generally speaking, what one sees in cupolas or porphyries is the majority of the mineralization is associated with hydrothermal stockwork or sheeted quartz veins. Not always. It can be as disseminations in micromarulitic cavities, which is basically the magmatic to hydrothermal transition. It's just frozen, and you can have overprints on. You could have mineralized USTs. You could have mineralized sheeted quartz veins, and you could have mineralized marulitic cavities. But dominantly, generally speaking, the mineralization is associated with the hydrothermal quartz vein event.
Okay. Another question from Martin. How small can be a magmatic feature to produce a UST?
Another good question. I mentioned midway through the talk that the dimensions of the UST zones vary a lot. Typically, they're small, and they can be as small as a television set. But it's important to recognize them. Why? Because it's telling you you're at the top of an overpressured volatile and fluid cupola. So careful observation is really key. But the size range or 3D dimensions of the UST zones varies tremendously, as do, I hope I showed, the textures. So the second slide or third slide I showed with those beautiful parallel bands is atypical. Generally speaking, the textures are more like what I illustrated from North Parks and some of the other porphyries.
Okay.
I hope that answers the question.
This one is in Spanish.
Yeah, translate for me, please.
Okay, no problem. Can the development of USTs occur in intermineral intrusion cupulas, or do they only form in zinc mineral intrusions?
They can form anywhere in the intrusion, but because they form under magmatic hydrothermal overpressured events, generally it would be intra and syn.
Okay. No,
And that's a good question, because what happens often is that once the USTs are formed in those intrusive phases, they often get obliterated or destroyed by the overprinting mineralizing event. So you have to look carefully. Sometimes if you look at your drill core that shows beautiful stockwork veining, try to look through or below the stockwork veining in your drill core to see if there's any USTs, because I've often observed drill core with sheeted or stockwork veining, and when you look carefully, it's actually overprinting an earlier UST event right at the beginning of the formation of that particular intrusive event.
Okay.
If that makes
Another
sense.
question from Agatha.
Yep.
According to your experience, based on your experience, have you seen more than one level of USTs develop in porphyry systems?
Another good question. The answer is yes. and particularly in porphyry moly systems. At Henderson, for example, there are stacked zones of USTs reflecting multi-pulse events with time. And also I've seen examples elsewhere. One porphyry in particular in southwest US where there were stacked UST horizons. It's not common. I have to say that it's the exception rather than the rule, but it does occur.
Yeah. Okay. Now there's a question. Well, I'm interested in this question, and I will ask you another thing based on that. How do pressure variations affect the morphology of USTs?
Oh, another good question, because they often show ductile deformation as shown in those convoluted bands. So I suspect that, yeah, maybe no, I don't have a direct answer for that actually. It's a good question, but they're obviously a very dynamic environment because mostly the UST bands are convoluted. They can be broken up. They can form clasts in carapace breccias, but as to how we actually form those convoluted bands is a really good question, and I don't have an answer for that.
Yeah. Okay. Also in the paper you mentioned at the end, yeah, there's the textural types of the USTs. You can see the striated granular, fragmented, bichated. I would like to ask you if these textural types are associated to, we can associate that with ore grades, with mineral grades.
Not really. I don't think there's a direct correlation because it depends on the strength of the volatiles and fluids, the event, the size. No, I don't think there's a direct correlation to grade. What is interesting is when you see USTs that have, I mentioned earlier, that have magnetite and they have sulfides. For me, that's always a very good sign. So I'm excited when I come across in drill core, if I see USTs that have a lot of sulfides and magnetite, it might not be a very big deposit, but it could certainly be a high grade one. And Ridgeway in the Lachlan Fold Belt is a great example of that.
Yeah, okay, there's three questions more, and also someone want to speak. We will end with this.
Yes.
Okay. Quartz in silica caps replace earlier minerals or fill open spaces like miarolitic cavities.
On the cartoon I showed, the cupola cartoon, the marolitic cavity zone generally is, well, it always is below the magmatic quartz silica cap and the USTs. And basically what we're doing, we're not allowing the volatiles and fluids to escape into the wall rocks. So the confining pressure of the cupola is such that the magmatic volatiles and fluids can't escape, and they slowly but surely crystallize below or in the lower part of the cupola and form a disseminated style of mineralization. And several porphyry copper deposits display this, but bearing in mind that you can have multi-phase events so that a subsequent event could overprint hydrothermal veins, breccia pipes, all different kinds of things. So these are dynamic systems, but marolitic cavities, mineralization in marolitic cavities tends to form in a relatively passive environment where everything's combined and essentially the whole mineral system shuts down.
Okay, the last two questions. What happens after the UST when a silica zone with little mineralization is found? Does this indicate a poor system, or should I continue drilling in another direction?
Good question. If there's nothing in the massive quartz silica cap, I wouldn't drill underneath it. I'd take out my boots and hammer and I'd prospect 5 kilometers in every direction, or maybe 10 kilometers in every direction away from that barren silica quartz cap. I wouldn't drill under it.
Okay, okay. The last one. Since USTs are made by fast crystal growth in magma that's very full of gases, how can you tell them apart from textures formed by quick cooling near the surface, where the pressure is very different?
I think what well, they're two different environments. One is magmatic, and then once you're in the near surface lower temperature environment, you're actually in the epithermal regime. So below 500 degrees or 450, you're transitioning down into epithermal temperatures and pressures, especially pressures. And the textures are completely different. So what you would then see would be all your classic spectrum of epithermal vein textures or quartz vein textures.
Okay, now Yuder wants to talk. Yuder, you have the microphone now.
Okay, thanks. Awesome presentation, Dr. Douglas. Thank you so much. I would like to download all your knowledge to my head. My question is, environments that we can find UST texture and why?
I missed the first part, I'm sorry.
Yeah, could you repeat that, Yuder, please? I also missed the first
Yes. Which are the most common and less common tectonic environments we can find UST texture and why?
Okay. Well, essentially, wherever you have the tectonic environment where you can form intrusion-related ore deposits, and that could be a rift setting such as the big porphyry moly deposits, or it could be back arc, island arc, any environment where you have the capability to form evolved felsic magmas. And it's simple. There's a wide variety, but in terms of the tectonic setting, anywhere that's capable of forming felsic magmas, differentiated felsic magmas. And so if you look at the variety of tectonic settings for intrusion-related mineral deposits, there's a whole spectrum, and any one of those is capable. As long as you have the potential to form evolved felsic magmas, you have the potential to form those cupolas with the associated textures. It's a broad answer to your question. I don't think there's any specific environment per se, as long as you have potential to form evolved felsic magmas. And that covers a very wide metallogenetic spectrum from tungsten, tin, rare earths, uranium, copper, gold, molybdenum.
Thank you so much, Dr. Douglas.
Yep.
Okay, Justin, I will share my screen.
Yeah, please.
Okay, tell me if you can see it. Okay, Douglas, on behalf of the SEG-UCE FIGEMPA student chapter, we sincerely thank you for sharing your expertise with us today. We truly appreciate your time in contributing to our academic formation, and as a token of our gratitude, we would like to present this certificate of appreciation, which reflects our deep respect for your contribution to our chapter. And once again, thank you all for being today, and we look forward to staying in touch and hope to welcome you again in the future. Thank you very much, Douglas, and thank you to all the attendants for your comments and questions.
Thank you, Stalin, and thank you to all the attendees. It was a real pleasure, and I wish you all the best and success in your forthcoming careers. And as I said, please contact me anytime if you have any questions, whether it be technical or about your careers. I'm actually one of the SEG mentors among many, and I highly recommend contacting people in the SEG mentor program. There's literally dozens of people willing to share their experience and knowledge. Multilingual, there's many Spanish-speaking mentors, so I'd highly encourage you to take advantage of that. And yeah, thank you very much. So good luck for everybody.
Thank you, Douglas. Thank you. Yeah, good morning, Dad, and good night here.
Yeah, thank you.
See you next time, Douglas.
Yeah,
thank you, everyone.
Bye-bye.